Alrighty, so today we are going to quickly run through the first part of these factoring special products notes. And for the warm-up, they want us to find each product. Essentially, all that means is we are going to start foiling these things, aka we are double distributing here. Now, hopefully we're noticing a little bit of a pattern right off the bat. I have an x plus 5 times an x minus 5. I have an x plus 7 times an x minus 7. And then lastly, I have a 2x plus 1 times a 2x minus 1. So what's in my parentheses looks pretty darn similar between each binomial. The difference is just the sign in the middle. So let's go ahead and see what happens when we actually go through and FOIL it. So x times x gives me an x squared. X times negative 5 is a negative 5x. 5 times x is a positive 5x. And then lastly, 5 times negative 5 gives me a negative 25. So when I go through and I collect my like terms, well, this negative 5x plus 5x is leaving me with 0 x's. Essentially, those two terms are just canceling out one another. And so when I write my simplified answer, I am only left with these two terms, an x squared minus 25. We can notice something similar when we go through and FOIL the next one. So I have x squared minus 7x plus 7x minus 49. Once again, we see that these 7x's are canceling one another, and so we are left with x squared minus 49 as our final answer. And then lastly, when we FOIL these last sets of parentheses, I'm left with a 4x squared and then a minus 2x plus 2x minus 1. And sure enough, once again, my middle terms are canceling out one another, and 4x squared minus 1 is what I am left with. And so that's today's main idea, is that now we are undoing things that have been FOILed that are leaving me with a binomial here. And specifically, what we call this is a difference of two squares. So a difference of two squares is something that resembles this format. I have something that we're calling a, which is squared, minus something that we are calling b squared. And if I am left with a binomial that consists of two perfect squares, then we can factor this as a plus b times a minus b. So if we go back, we sort of see that happening, right? A and b are x and 5 over in this first example, so I have x plus 5 times x minus 5. Well, my final answer was x squared minus 25. So now we're going backwards and finding what did we start with these two parentheses. Couple of things to note here. Number one is that this is only something we use with binomials. So things that are two terms. Number two, these are things that are only perfect squares. So if either of these terms in my original binomial are not a perfect square, then we cannot factor with this a plus b times a minus b. And the last condition that needs to be met, number 3, is we need to be subtracting. We need subtraction, specifically right here between this a squared and b squared. If I have something that says a squared plus b squared, we are not going to be able to factor it using this method, because that subtraction is what essentially is allowing us to have opposite signs in our factors, and those opposite signs are what end up canceling the middle term. So anytime we are missing that middle term, so if I have a trinomial, ax squared plus bx plus c, and I do not have the middle term, that's a good indicator that, number one, if this is a negative here, then we can be looking for using this sort of method of factoring, a difference of two squares. It's going to be very helpful for us to know all of our perfect squares. So real quick, we'll run through those. 0 squared is just 0. 1 squared is 1. 2 squared, 2 times 2 is 4. 3 squared, it's not 6, it is 9. 4 squared is not 8, it is 16. So make sure that you are squaring these things. We are not doubling them here. 5 times 5 is 25, and then 36, and 49, 64, 81, 100, 121, 144, 169, 196, and then 225. So the more comfortable you are with your perfect squares, then the easier this difference of two squares factoring is going to be for you. So here we go. We are going to factor these binomials. Now, as we've talked about, finding a GCF is still our priority. So if there is a GCF for us to find that's not 1, then we are going to factor it out. So we still want to go into these problems looking for the GCF first. Now with number 1, I have an x squared, I have a -4. Obviously there's nothing in common that we can factor out between those two, so let's look if we can use perfect squares. Well, number 1, it's a binomial, so that meets one of our conditions. Number 2, I'm seeing that there is subtraction in between these two terms. And then lastly, number 3, both of these terms are in fact a perfect square, because I know that the square root of x squared is just x, right? X times x gets me that x squared. And likewise, the square root of 4 is 2. So we're going to be good to go to use our difference of two squares method. So I get my parentheses set up. I know that this is going to resemble a plus b times a minus b. So one of these will be positive, one of these will be negative in the middle, and then the a term is just my first term, the square root of that. So we found that right here. Square root of x squared is just x. So I fill that into the first slot of both parentheses. And then the second slot of my parentheses we find by taking the square root of our second term in our binomial, which we did right here. So that's going to be a 2 that we fill in. And so then that's my final answer. X plus 2 times x minus 2. And once you recognize this pattern, these go pretty quickly, because there's not really a whole lot of thinking that we have to do. We can just kind of run on autopilot. So once again, with B, I'm looking, do I have a GCF? No, y squared and -49 don't share any common factors. So we're going to go with using a difference of two squares, because once again, I have a binomial, I see subtraction in the middle, and I, in fact, have two perfect squares. So all we're doing is square rooting each of those terms and filling those into my parentheses. So y squared results in a y times y, 49 results in a 7 times 7, and then to match our pattern, one of those 7s has to be positive, one has to be negative. And as always, we can go through and check these using FOIL. Example number 3, we have w squared minus 81. Well, 81 is a perfect square. It is 9. The square root of 81 is 9. So we can fill those in, and w squared comes from a w times a w. And so we're done. And you're going to see that as you start to work with these more and more, they are very, very straightforward. There's really not a whole lot for me to explain here. So essentially, it's just, can you recognize when these problems are set up for us to factor them in this way? So there's D, E, and F right there. I want you guys to try G, H, I, J, K, and L right now. Go ahead and pause the video, give those a shot, and then you can check your answers with me. Hopefully you actually did that. And here's your answers for those 6 problems. Quick thing to know is when I do have a coefficient on this first term here, like this 4x squared, we do have to square root both of the 4 and the x squared. So that's going to leave me with a 2x. Same thing over here, the square root of 81x squared. Well, the square root of 81 is 9, and then the square root of x squared is x. And so that's where we're getting those coefficients that are not 1 on these x terms in front here and here. And other than that, that's honestly pretty much it. Now, just like I said before, our priority is to check for a GCF every time. So if we see something that looks maybe a difference of 2 squares, sort of, but it's not quite there yet, again, that's why we are looking for the GCF first, because looking at example A here, I see a 2x squared and a negative 50. I know both of these are divisible by 2. And so that's what we are going to start by doing. We are going to factor out the 2 first. Then I'm left with x squared. Negative 50 divided by 2 is a negative 25. And sure enough, as soon as we factor out that 2, now I'm left with something that resembles that difference of 2 squares setup. So we can factor that even further. And then we just carry this 2 down in front. And so this right here is my final answer in total. To see another example of that, I'm looking between these two terms. They share a 5. So we will factor out that 5. Now I'm left with n squared minus 9. And once again, I can go ahead and factor this as a difference of 2 squares. So n plus 3 times n minus 3. And lastly, that 5 stays out in front. Don't forget about it because it's still part of my final answer. Pretty obvious here to see what's going on with this last one. We can factor out the 2. So I'm left with r squared minus 1. And then we can factor that further to a r squared plus 1 times just r plus 1 times r minus 1. And there we go. That's about it with difference of 2 squares.